In today's lecture, we're going to build on what we've been discussing with our spin 1/2 systems to general systems, general spin systems, and paying particular attention to the spin 1 system. So with general spin systems, like I say, we've been discussing the spin 1/2 system because it's a great sort of simplest system we can use to introduce all these concepts. With general spin systems, we're going to need to know two quantum numbers to label that spin state. Right? One is S. It's the spin angular momentum quantum number that essentially is what's the total, like the spin type of system we're looking at. Is it 1/2? Is it a spin 1, a spin 0, a spin 2? What is the spin type of system we're dealing with? And then there's M, the magnetic moment quantum number, or the spin component quantum number, which is what is the state that it's in projected to the basis you're looking at. So if it was for the spin 1/2 state, we were either spin 1/2 or spin minus 1/2. So the general system ket describing that system will now have two numbers. S for the spin angular momentum quantum number, what type of spin system is it, and M for what is the actual spin component of that system. So if we have that state and do a Stern-Gerlach measurement with it, the number of beams we're going to get is going to correspond to 2 times the spin quantum number plus 1. So in our spin 1/2 systems, we had 1/2 times 2 is 1, plus 1 gave us 2 beams. We had the spin up and the spin down beam. The eigenvalues of that system range between minus whatever the spin is times h bar, so that was minus h bar over 2, all the way up to positive the spin times h bar, so that was positive 1/2 h bar, and it takes steps of h bar. So again, in our spin 1/2 system, this was pretty straightforward. It just went from minus h bar over 2 to plus h bar over 2. In this sort of SM notation, what we've been calling the spin up in the z basis state would be 1/2, 1/2 in the ket. So the first 1/2 is S. It is, we are dealing with a spin 1/2 system, and it is in the plus 1/2 system in the z basis state. The minus, or spin down ket we've been talking about would be 1/2 minus 1/2. Again, it's a spin 1/2 system, and we're in the spin down state. If we were to look at a spin 1 system, we would have 3 different beams corresponding to those 3 eigenkets in our Stern-Gerlach experiment, because 2 times 1 is 2, plus 1 gives us 3 total number of beams. The beam corresponding to the spin 1 state would be written here as 1, 1. The corresponding 0 state would be 1, 0, and the minus 1 state would be 1, negative 1. Again, the first number, the same for all of them, because they're all describing a spin 1 system, and then the different spin component values for the second quantum number. Now, if we stick with that spin 1/2 system and look at the z bases and do our Stern-Gerlach measurement, we're going to have written in the ket notation, there's going to be some operator S sub z, just like there was with our spin 1/2 system, that has an eigenvalue equation for that spin in the z component Stern-Gerlach measurement. And that eigenvalue equation is going to look like this. Likewise, for the spin 0 state and the negative 1 spin state, where we have the 3 eigenvalues h bar, 0 h bar, and minus 1 h bar acting on those states. Now, if we want to write this in our matrix representations, well, we know that in a given operator's own bases, that those those eigenkets are just unit vectors. So the 1, 0, and negative 1 eigenkets for the spin z operator are just going to be these 3 unit vectors in the matrix notation. We can likewise, we know the spin z S sub z operator is going to be diagonal in that basis with the eigenvalues along the diagonal. So we know that the matrix representation of that S sub z operator is just going to be this. Now notice zeros in the middle there along the diagonal. 0 is a perfectly valid eigenvalue, so that's not an issue. But there we have it. We have our SZ operator in matrix representation and the SC eigenkets in the matrix representation. A question comes, though, is what about the X and the Y bases? And we can do the same sort of thing we did with our spin 1/2 systems to sort these out. We could run a bunch of Stern-Gerlach measurements, have a S sub Z Stern-Gerlach analyzer and then take the spin 1 beam, send that into an X Stern-Gerlach analyzer, and what we would see is the probabilities of measuring the spin 1 in the X direction state is 1/4. Likewise for the spin -1 state in the X direction, and the spin 0 in the X direction would be a 50% chance. We also know that those eigenkets for the Z bases, the 1, the 0, and the -1 in the Z bases, form a complete set. So we can describe any general system ket as a linear combination of those, just with A, B, and C as complex numbers. So we can write our spin 1 in the X direction that way, as a linear combination of the 3 spin Z states. Likewise for our spin 0 and our spin -1 in the X direction states. Now, one thing we have to remember is that A, B, and C are complex numbers. So these probabilities, they do give us some information about what they are, but they don't give us everything, right? We know that the probability of measuring the spin 1 in the X state is given by this, according to postulate 4. And if we take that inner product, well, if we take the 1 state and multiply, or bra, and multiply it by this ket, well, 1 and 0 are orthogonal, so that would just be 0. Likewise, the 1, -1 states are orthogonal, so those would be 0, and we'd be left with just A, and that probability is equal to the magnitude of that complex number A squared. Likewise, the probability of measuring the 0 state is B squared, and C squared. That only gives us the probabilities, the magnitudes of these coefficients. Right, we need a little bit more information to totally get the information of that state. So, but if we do this and then we do other Stern-Gerlach measurements, throw the 0 in there and the spin -1 state in there, and look at all those probabilities, we can determine the magnitudes of all these coefficients. And what we would end up with is the A, C, G, and J coefficients have a magnitude of 1/2. The B, F, D, and H have a magnitude of 1/√2, and the E has a magnitude of 0. But what about the phases? All right, well, to get the phases, we have to use something else, and it turns out we can use orthogonality, right? We know that the eigenkets coming out of this S sub X analyzer, they're going to be orthogonal to each other, right? They form an orthonormal set of vectors. So if I look at any of them taken with the inner product with themselves, they're going to be 0. And I can use that information to sort of solve for the phases of these basis kets. There is some freedom to choose some value of the phases because, if you think back to our position unit vectors, if I define one of those basis unit vectors, say z hat, there are any x hat direction in a whole given plane is orthogonal to that, and you have the freedom to sort of choose that. That's similarly to that, there is some choice here. But anyway, you go through all of this, and we get these three, the eigenkets for the x S sub x operator written in terms of the eigenkets in the z bases, right? So this is our x bases vectors written in terms of our z bases, and we can do the same thing for our y bases. The y bases basis kets written in terms of our z basis kets. Moving on to that, we can also do the same sort of thing where we can write the s sub x and the s sub y operators in this basis, and we can get the matrix representations for them. We know that this s sub x operator acting on any of these kets, but we'll look at this one, for example. S sub x acting on the spin 1 in the x direction ket returns that eigenvalue h bar times that same ket. Likewise, acting on 0 and minus 1, we can use those equations to get to basically sort out what this matrix representation it is for the x operator. Likewise, for the xy operator. Once you have all those, you have all the tools, and we can do everything sort of that we did with the spin 1/2 system, just using the same tools in a higher dimensional space with the spin 1 system. So let's look at just a simple example of this. Consider some spin 1 state, some general state that's written as this. It's a superposition state of the eigenkets in the z bases. And you could ask, well, what are the probabilities? What are the 3 possible measurement results of an S sub z measurement, and what are their probabilities, right? Well, the possible measurements are the eigenvalues for each, for that S sub z operator, which are h bar is the first one for the spin 1 state, and the probability from postulate 4 is just this, the inner product of the measured outcome state with the input, the state you were measuring all squared. If we look at that, the inner product of 1 with this whole state, again, the 1 and 0 are orthogonal, so that term would be 0. 1 and -1 are orthogonal, so that term would be 0. And we'd be left with just this coefficient here, the magnitude of it squared, which is going to give us 1/6. Likewise, if we look at the 0 h bar eigenvalue, or the probability of measuring it in the 0 state, we just take the inner product of that 0 with that general ket, and we get this magnitude squared, which gives us 2/3. And finally, the -1 or minus h bar state, same thing, and hopefully you can see how that's going to be 1/6. Right. So for spin 1 systems, we just kind of showed and went through what the basis kets are for the different S sub z, S sub x, x sub y bases and operators, and we can do all the things we did with the spin 1/2 system. This maps to that sort of things we're doing maps to just general quantum systems. Let's say you have some n-dimensional system with some observable A. That observable A is going to have an eigenvalue equation like this, where the A is going to act on some eigenket, the nth eigenket, and it's going to give the nth eigenvalue times that eigenket. And we know a few things. We know that that in that basis, the basis formed by these eigenkets, that A operator is diagonal with the eigenvalues along the diagonal. We also know that the basis vectors, these A sub n, are just going to be unit vectors in that basis. And that we can form projection operators from each of those eigenkets. That's just this outer product of those eigenkets. And finally, those eigenkets form a complete set. The completeness holds, right? So the sum over all of these projection operators is equal to the identity matrix, which is the same thing as saying I can write a general system ket in terms of a linear combination of those eigenkets. If I just take that, the general system ket and multiply it by the identity matrix, which is all those projection operators, I get this. Each one of these inner products of the eigenbra with that state ket gives me some complex number, C sub n, and now I've written this general system ket in terms of a linear combination of these eigenkets for that operator. And we can do this with quantum systems. So hopefully by now we're done chapter 2. We've sort of developed the tools to describe quantum systems, and that one thing we haven't done though is discuss how these systems change with time, and so what is the time evolution of these systems and what determines that. It turns out that's the Schrodinger equation, and we're going to get onto that in the next video.